Hello, everyone. Welcome to Systems, or Vancouver Systems. I almost said Systems Distributed, which is a great conference if you're into system stuff. I highly recommend it. Today, I'm going to be talking about storing small things in big places. Came up with this talk title, I don't know, the shower or something, and I was like, that is such a cute title. I have to use it. So then I wrote the entire talk based around this title. So that's the plan. My name is Sverre. I have been working in databases for 12 years. I worked at a company called SingleStore, which is a distributed relational database based around, or it simulates basically MySQL, but it provides all these cool distributed systems properties. And about 2 years ago, I decided to quit that and start my own thing. And so I've been sort of exploring some ideas I have in data for the last 2 years. And today I want to share my most recent project that has not yet launched. I'm hoping to launch it this month. So this is very exciting. I've been working on it for about a year. Yeah, this is the first time that it's been publicly shown in any way. So just to go back to 2023, so about like 8-ish months after I quit my company, my previous company, and started going on my own, I launched something called SQLSync. Show of hands, does anyone know what SQLSync is? Okay, sweet. We got a couple people who've seen SQLSync. So SQLSync is multiplayer SQLite. So if you're familiar, so SQLite is a really simple relational database. It's embeddable. It goes right in your application. And I really wanted a multiplayer version of it. I wanted to be able to have SQLite running in like browser tabs on devices, in serverless edge functions. And I wanted to be able to have all of those just synchronized in a really nice way and lead to a sort of like offline first user experience where you could build applications that were local first, but you still have all the power of SQLite. So I prototyped this idea and launched it at the end of 2023, and I got a lot of really good traction. Like I think it went really well. A lot of people found it really cool. However, when I went to actually go to the process of turning into a real product, turning into something that people could use in their application, I realized that the backend that I had built was just not going to scale. And for fair enough, like I didn't really design it to scale. I designed it to show off an idea. However, it forced me to ask the question, like, what would be that backend that I would need? Like, what would be like the ideal backend to make SQLSync work? So I really went back to the sort of drawing board and started to like write down what would that look like. And I came up with sort of this description, this very abstract description. Basically, I wanted transactional object storage. Like I want like an S3, except I want it to be able to be transactional. So I want to be able to issue arbitrary partial rights to blobs. And like edit them essentially. I wanted them to be able to transaction, and I wanted to be able to efficiently replicate those changes out of those blobs to the edge. And even more interestingly, I came up with these 4 properties, which I'm going to say lazy, partial, edge, and replication. So these are my 4 properties, and I'm going to define them really quick so that we are all on the same page about the ideal backend for SQLSync specific use case. So lazy, partial, edge, replication, here we go. First, lazy. Clients choose when to sync. So in an offline first or a local first use case, you don't have the flexibility of always being online, being able to receive, for example, like a full blast of a change log from a database. You might only be able to sync here and there, maybe when you have internet, maybe when it makes sense. And so we have to be able to have a system that's okay with clients potentially not syncing very frequently. And even more importantly, when they do sync, we want to maximize the value we get out of that sync operation. So we don't want to necessarily force, like if we edit a row in a database like 500 times, we just change the value of the row 500 times, we don't want to force a client to download all of those 500 changes just to see the latest value. We just want them to see the latest value. So we want this idea of essentially rolling up changes and this idea of lazy synchronization. The second property is partial. So I want to be able to allow clients to choose which subset of the data that they actually sync, they actually download. Oh, did I lose? No, can everyone still hear me? Yeah. Okay, cool. Cool. So I want to be able to have clients choose what subset of the data that they actually get. What this means fundamentally is that if we want clients to be able to efficiently sync and replicate data, they have to know about what has changed without knowing all of the actual individual changes. Like we can't just send them all the changes because then they're essentially getting all of the data. We have to send them sort of a description of the changes so that they know what's changed, and then they can choose which subset of the data they actually end up getting, right? So this is the idea of partial in my world, partial replication. The last property, or sorry, the second to last property, edge. So this, in my use case, is clients choose where to sync. What this means for me is that the client code, like all of the code that runs on the client, is lightweight and embeddable enough that we can run it in really small places. We can run them in serverless functions. We can run them in web browser tabs. It means that maybe it's WASM-friendly code. Maybe the storage engine is very pluggable. All of these different properties go into making the software easy to use in lightweight places. And this was very important to me. And the fourth property, I don't know why it says volume there. Just pretend the volume word doesn't exist. The fourth property is essentially replication. So this is the most common property in distributed systems and especially databases, just the idea of having essentially two different places see a consistent view of some data. Now, when I say consistent here, I want to be very clear. I'm talking about internal consistency. If I look at a snapshot of a file, the internal state of that file, if there's pointers in that file to other regions of that file, all those pointers are consistent with that version of the file. So I'm always looking at a snapshot of the data. So this is the specific kind of replication. So essentially I want snapshot isolation and the ability to sort of see snapshots over time on clients. And I want to guarantee that if two clients have the same reference to the same snapshot, they see the precisely same data. And that's a very important property that SQLSync depends on. And in terms of sort of the architecture constraints that I have in my system, I want to optimize for cost and reliability, potentially at the expense of performance. So I'm really optimizing for like high scale out, low cost. And that's one of the reasons why I use object storage extensively in my solution or in my project. Okay, so with these criteria in mind, I sent out on your standard software engineering search for software. You start reading GitHub repos and READMEs and like going through marketing pages and trying to like pare through all of the, for the lack of the better word, bullshit that mostly doesn't explain what things do. And finally you get down to like maybe a short list of a couple of technologies, you play with them. Ultimately, after all this work, I just couldn't find something that was satisfactory. I didn't find anything that hit all of those properties that I explained and was also lightweight and was able to run inside web browser tabs and was cheap and had like the same performance characteristics or durability characteristics that I was looking for. So, like all excellent software engineers, I built it myself. All right, introducing Graft. This is my logo I created in Excalibur. Graft is, let's go to the next slide. Graft is a transactional volume store supporting lazy partial edge replication built on top of object storage. Basically, Graft is like S3 if it had transactions. That's sort of the general gist of it. I called it Graft. Like, I would love to get a show of hands if anyone sort of resonates with the name Graft with this description. I'm going to say like 45%. Okay, cool. Name is going to stay. We're good. So Graft, I had to come up with some terms. We're computer scientists. We love naming stuff. So like, I was like, okay, well, what am I going to call this like thing that Graft like synchronizes? We're going to call it a volume arbitrarily. I just like that word. Volumes in graphs are sparse ordered sets of pages. Sparse is actually really nice here. If we have a volume that contains like a huge section of like empty space, we don't actually store anything. We just say it exists and Graft figures it out intelligently, supposedly. So it's a sparse ordered set of pages. Pages are indexed just like 1, 2, 3, 4. It's one base indexing, which is really weird in computer science, but I could go into that later, but I have like a really interesting reason for that. I'll talk about it after if you're interested in that. That's a long conversation. Okay, so long story short, we have volumes, sparse order set, and this image is just like a very abstract representation of like a SQLite file, right? So going back to my favorite database, SQLite, SQLite stores data in B trees, which are these really nice data structures that map down to pages. And so this sort of image with all these boxes, if we imagine each box is like a page, each color is like a separate B tree. So we could see how one volume can store like multiple B trees by just sort of organizing the pages in a particular way. Graph pages are really small. So everyone in this room probably has heard of pages either via like memory or like file system blocks, or, there's lots of pages show up lots of times in software. In my world, a page is simply a fixed size block of bytes. And in Graft, it's specifically a 4 kilobyte block of bytes. And I did that out of simplicity because I'm trying to launch this month. But I do have a plan on making this more variable in the future. So that's sort of the next step. Okay, so we've blasted through and on reasonable time. The goal here is to go through the architecture of Graft at a pretty high level. So I'm going to start with like an eagle-eye view. And then we're going to go into like more low level of the 4 individual sort of phases of a transaction and replication process in Graft. And I encourage you during those 4 stages to ask questions. Just keeping in mind, we're going to go to the next stage. So like if your question's about the next thing, wait till that slide. But yeah, if there's any questions about like those particular stages, I'm happy to do that. And then after that, we'll be doing a quick demo, hopefully. Okay, so this is the eagle-eye view of Graph. This is all the stuff I wrote at a very high level. On the left side, first of all, the left side and the right side are the same code base. Like there's a client code base and the server code base. The client code base is bidirectional sync, so everyone has the ability to read and sync data back to Graft. But for the purpose of this explanation, we're going to say that the client on the left side, we're just going to call them arbitrarily the writer. And the client on the right side, we're going to call them the reader. And we're going to talk about these 4 sort of transactions that occur. So I've labeled them 1, 2, 3, and 4. We'll talk about each of those 4 transactions. And the 2 transactions on the left are essentially the write transaction. So this is how you mutate and commit a new volume snapshot. And the 2 transactions on the right is essentially the reader transaction. So this is how you pull and learn about changes, and then you actually go and look at those pages that have changed. Right? So that's essentially Graft. It's a relatively, when you look at it like this, it's so simple. Like I wish I had this a year ago. It's beautiful. So in the middle, we have just 2 services. I split this up purely out of, maybe over engineering, but also just the ability to run services in different places. There's a little bit of distributed system stuff here, but that really doesn't matter for the purposes of this talk. Basically, I have 2 concepts in the server. I have a page store and a meta store. And really, it's sort of on the tin. Page store literally just stores pages. It doesn't even know about snapshots or versions or anything. It's just like, I got pages, and it makes them durable. And it uses our favorite thing ever, which is S3 or any object store, to make them durable and just make them work. S3 gives us all these great advantages like crazy high throughput, very, very high durability. And most importantly, I don't have to explain to anyone how it works because everyone knows how it works. So that's the main thing. On the Metastore side, we actually maintain the commit history of a volume. So if you think of a volume change over time, our goal is to maintain these like snapshots and allow clients to see these snapshots. The Metastore only cares about the metadata of those snapshots, essentially the version number. So it's just 1, 2, 3, 4. And the set of segments, which we'll get into, and the set of offsets that have changed inside those segments. And essentially, that's all the Metastore deals with. And for simplicity and for durability, it also just commits an object store. And so one thing you may wonder is like, what's the performance of this thing? And the performance of this thing is very limited by object storage. And that's like on purpose. Again, SQLSync's use case is not designed to be real-time, high-performance, like you commit a transaction, you immediately see the transaction in every replica. The goal of SQLSync is essentially async offline first replication. So if it takes a second for us to wait for data to replicate, I'll get to your question in a second. If we can fly a mic over here, that'd be awesome. If we are waiting a second or a couple seconds for data to sort of sync and flush all the way down to object storage, that's actually okay in our use case. We get so much advantage of durability from object storage, it's worth the trade-off. Question?
Yeah, wow. Just to make it kind of maybe a little bit more concrete for the rest of the talk, what are a couple of products you can imagine people building on top of this? So like where would this fit in? Where would it be a good fit?
Yeah, awesome. So everyone here has lots of like cool phone apps. Apps running on your phone do tend to have like an offline first sort of style of how they work. They tend to have sort of snapshots or cached versions of state locally that they try to use as much as possible to basically improve the user experience. You're not sitting there waiting for loading screens constantly. So think about like any sort of data heavy phone app. like a task management tool, like a Jira, could use something like this, like an offline first. Similarly, in the browser, browser apps are becoming more and more sophisticated with the advent of like WebAssembly. We're seeing like things that look a little bit more like desktop applications where we want that like local latency that we get of traditional desktop applications in the browser. We're starting to see that happen more and more frequently. Some of these want like very custom, almost like unstructured data storage solutions. Some of them want very structured data storage solutions, like a relational database, like a SQLite. Currently, if you want to use SQLite in these cases, you are in a little bit of a bad place because there aren't good sort of essentially the multiplayer problem of SQLite is not a very well solved problem. So if you do want the ability to have multiple writers to the same SQLite instance, it's tricky. So anyways, long story short, it's like any sort of device app that leverages structured data would be, I think, a good use case for Graft and potentially for SQLSync.
So just to clarify, it's generally where the amount of data for any given tenant is relatively small, but where you just have so many tenants, or you want it to be so cheap per tenant that you want the data to be in blob storage. And you want that like ability to not really worry about how many tenants you have.
Yeah, I think that's a pretty good way of looking at it. Generally, SQL Sync definitely benefits from like many instances of a database versus one gigantic database. Graft does have one aspect of Graft, which I've worked really hard on and actually works really well, is this concept of partial replication, where you can have like a 10 gigabyte SQLite file. And if you have well-crafted indexes, SQLite actually does a really good job of only downloading a very small fraction of the data if you're only looking at small amounts of data. So if a user is only looking at a single row and maybe all the foreign keys to that row or a couple of rows, SQLite will do a really good job of not reading the whole file. And so Graft is designed for that use case as well. Cool. So we have the high level stuff here. Let's go and talk about these 4 sort of quote unquote transactions or phases really quick, and then we'll get to a demo, and hopefully we have time for questions. Okay, so the first phase is simply the durability phase. So the key thing here is that when a client changes a database, it just uploads those pages and that's it. It doesn't, essentially it's not worried about versions and transactionality at this point. It's only worried about durability at this point. So the client can connect to any page store worldwide. Page stores run inside a distributed system called fly.io, and you can just persist those pages into fly.io. Well, into the page store. And the page store internally, these page store instances that run geographically distributed, they internally buffer up many pages from many different writers into one thing called a segment. And the idea here, and this is a very common pattern when people tend to put small things in object storage, is that the cost of essentially putting a single object into object storage, just the cost of the put request is pretty high. But if you put a lot of bytes, like if you can sort of collate or amortize a lot of put requests into one big put request, you can really minimize that cost. So the page store basically sits there on like a sort of ticker, and every single page store worldwide will just sort of wait and flush and buffer up writes at about a second granularity. So that's just sort of the write process. Once pages reach the object storage in these things called segments, what comes back from object storage is essentially a list of segment IDs that contain the pages corresponding to the client's write request, along with which offsets the client uploaded exist in each segment. So now the client has like this really nice little bundle of information. I've uploaded like 10 pages. Those 10 pages have landed in 2 different segments, and offsets 1, 2, 3, 4, 5 have landed in the first segment, and so on. So the client just has like this nice little like bundle, and it knows at this point that this data is completely durable. It's being fully synced to object storage. Now the question is essentially, how do we commit this data into the next snapshot version of the volume? So this process, it's also relatively straightforward. The client takes that array of segment metadata, essentially this like sort of compressed set of the segments and page offsets that have been committed to the page store, and it sends it to the meta store, which is responsible for ensuring that the version number of a volume is monotonic. Essentially, like, well, it's not only monotonic, but it's atomic. So when the snapshot commits, it only lets a single writer essentially commit on a single snapshot version. To make this concrete, let's say the client's at version 1 of the volume and they want to make a write and transition the volume to version 2. They'll send to the metastore that, hey, I made this write. Here's like all the segment metadata. Here's all the page offsets that exist. And I made this write on snapshot version 1. If it is true that snapshot version 1 is the current latest snapshot in the cloud, then the metastore will be like, great, it will commit that. It uses modern object storage, have essentially cast semantics or compare and swap semantics on writes. So it uses that to basically atomically commit to object storage that there exists this new commit. And if it works, then essentially it tells the client, like, you're good. Like, your snapshot is now committed. You're now the latest snapshot version. And those page changes that you've made have now been incorporated in the like global log of this volume. So this is essentially the commit process. If there's a conflict, so if it tries to write and someone else has beaten it to it, currently the metastore just says, like, sorry, conflict, go away, like, you're wrong. Now, the client has something, a really cool property at this point. The client has a list of segments and essentially all the pages that it wrote. It also is able to go and retrieve the new snapshot from the server. So if we think about this, it can go download the new snapshot version that it hasn't seen yet. It can see all the offsets that have changed on the server side. And it can essentially do a variant of, MVCC, like multi-version concurrency control, locally. Because it has essentially its own read and write set that it knows everything that it read. It knows everything that it wrote. And so it can actually figure out whether or not the pages that it already uploaded to the page store are still valid or they need to be recomputed. And if it decides that this is true, it can actually just replay the commit on the new transaction or the new snapshot version, and it can immediately commit. So it allows us to do essentially client-side MVCC, which is a really nice property. It allows us to keep the page store very, very distributed, as opposed to forcing the page store to be centralized with Metastore. So this is the entire write process of Graft. Like, if no one has any questions, you are all Graft professionals. Any questions before I go to the read process? You can either yell or someone can fly you a mic.
You said that right after writing to the page store, it's durable. Are you actually waiting for the 1 second for it to flush to S3?
Yeah, so the writes are fully weighted on S3. A potential future, there's a question over on the left side there. Potentially in the future, what I might do is at a user opt-in, because there's a cost component to it. I will maintain essentially like a Raft consensus layer of fast like writers, essentially, where you can write to them, they'll immediately respond, be like, you've written, and then they'll internally maintain enough durability in memory or on like NVMe disk that they can essentially buffer and then flush to S3. So essentially, they just need to maintain enough quorum to be able to overcome the potential for failure between the write and the buffer. Yeah.
I'm really just curious how tightly coupled the Graft pages are to the SQLite pages. Like, can an SQLite page cross between multiple Graft pages? Does that create any problems? And like, would Graft work for things that weren't SQLite?
Good question. So the answer is Graft. When you use Graft, which I'm hoping all of you eventually do, when you use Graft, the API is very simple. It's just essentially put page, get page. And each page is essentially a 4K block of bytes. So if you can map anything to that API, whether it's a file or whatever, you're good. Now, there is a cost, like when you have misaligned pages in any system, and this happens, of course, in the file system quite frequently. Most file systems are block-based and have a fixed size. Essentially, you have this overhead of potentially having to read multiple pages to make a single write. If that overlap. And you potentially, in worst case, have to read and write multiple pages to simulate the write of a single page. So this is just like a reality of like a fixed size versus variable size things. But if you go low enough in almost any storage system, in many storage systems, you often will find this sort of fixed size problem. There's a lot of ways to solve it, and I do have some ideas for making it more flexible in the future, but right now I'm sort of limited. Your second question, does it work for other systems? Like, yes, basically. And in my experimentations with Graft so far, I've built a key value storage engine that's just like a really simple sort of like hello world key value storage engine. I've built, of course, a SQLite extension that is the full SQLite API on it. And I've experimented with some like fun little data structures. I've also just mapped file system operations directly to Graft as well. Cool. All right, great questions. Oh, there's another question. Go.
One more question real quick. Can you give me a little bit more information on what you mean by a conflict? Does it just mean that there has been another write since, and what do you do?
Yeah, totally. So basically, like, let's say you write, someone else beat you to it. So you thought the latest snapshot version was 1, but the actual latest snapshot version is 2. In this case, you have 2 choices. Maybe multiple choices, but the basic idea right now with how Graft works is Graft allows you to basically look at the state of the file in that new version that you didn't see before. So essentially Graft can like materialize on the fly multiple versions of a file at different snapshots. So essentially it says, hey, here's the file at snapshot 1, which is the one that you thought was the latest, and here's a snapshot at snapshot 2, which is the actual latest version. Are your writes still valid? If they're still valid at snapshot 2, then we just replay your commit and like you're good. If they're not still valid, you can go and essentially fix them and resubmit changed pages to Graft, and then Graft will essentially just send those like newer change pages, figure out the new sort of segment set, and then essentially replay the commit. So the goal of Graft is being able to do client-side like minimization of work by taking advantage of the client knowing a lot about what it's doing. Like it knows its entire transactional state. It knows all of its reads, all of its writes. And for a relational workload, this can work pretty well. Does that answer your question? Yeah, also, absolutely.
So it sounds like there's a new notion of like, is my write valid maybe in the API?
No, that would be like in the client app.
Oh, I see. Yeah, okay. Well, so the API that the client app is using.
Yeah, like the client app would decide if its write is still valid or not by inspecting the new snapshot version and cross-referencing the new snapshot version with its read and write set that it used to construct the original write.
Got it. Okay. So then it's the client's responsibility to submit.
Yes. And Graft is a client authority system, or it's like completely, clients have complete authority in Graft. Like if a client submits a bad write, it is the client's, that's up to the client. You can very easily write a client that just corrupts state. Graft will not stop you. Graft will just guarantee that there's a single global monotonic like set of version numbers that are strictly sequential. And Graft will not let you violate that. Cool. All right, let's talk about the read set, the read side. So on the read side, going back to that original sort of set of properties I was looking at. So remember, we want lazy, partial, edge replication. So the lazy piece is this top left of the slide where the client says, hey, I want to get all the changes that have happened since the last time I pulled. So this might be a month later, right, in an offline case. Conveniently, we have S3s backing us. So one of the big things about Graft in the architecture was get the cost so low for storing data over time that I can keep extremely long timelines of metadata to be able to fast forward clients to recent versions and really totally give them total knowledge of all the changes that have occurred since they originally synced, even if it was a really long time ago. There's some really nice bounding properties on that because we never have to store more data than describes the entire, like changing every single page in a set. Because essentially, if you change the same page 3 times, we only need to really know that it changed. We don't need to know that it changed 3 times. And that's because Graft it's not optimized for the case where you're jumping between a early snapshot and like a snapshot in the middle. Graft just is like, we're going from wherever you were to the latest version. And that's like how it's optimized. So the client says, hey, I'm interested in all the changes since some version number. The metastore looks in the object storage to make sure it's looking at the latest commit state. It does this because the metastore is also a distributed system that is stateless. So it assumes that someone else in the world has made a commit and it basically does a refresh. Once it does that refresh, it computes all of the offsets that have changed between the original client version and the latest version and sends down a compressed representation of that offset set and the new snapshot version to the client. So the amount of data the client receives, like assuming that, let's say the volume is 1,000 pages, the maximum amount of data that the client will receive is 1,000 U32s and a single U64. Right? So it's a really small amount of data to describe a very large amount of actual change that have occurred. So once the client receives that set, it's able to know, essentially it's able to record in its like local state that there exists this new version, and all of these changed pages since our last version, we have to go and retrieve those pages if we want to read them because they now exist at this new version. This is really important for like caching, because let's say that you have this like, oh, before I go here. Yeah. So let's say you have like this 10 gigabyte file stored in Graft, and the client, this one particular reader only cares about like the first 10% of the file. Whenever it pulls changes, those changes might happen to like the rest of the 90% of that file, but the client doesn't actually care about that portion of the file. Like it's never reading that portion of the file. And so in this architecture, the client will receive essentially the knowledge that those offsets change. So they'll be able to record in its local state, like, oh, there's new versions for those offsets. But it doesn't, that's it. That's the end of the story for replication. It can just move on with its life. And because these offsets are so small, like a bunch of U32s, we can compress them really well. Because they're so small, the cost of doing these pulls is very, very cheap. And so we can run this in very lightweight things like serverless edge functions. We can run this inside of browser tabs and so on. So now the client knows that a bunch of offsets have changed since the last version, and it wants to materialize a read operation at a particular snapshot. So the client internally, like in its local state, maintains a set of snapshots that it cares about. And it potentially maintains, keeps a lot of snapshots alive locally, because let's say you have like a huge multi-threaded program. Some of your threads might still be operating and running reads on a snapshot that has been previously downloaded. And like that's totally okay. Like in an offline first app, like this is a very common thing that happens. So Graft allows the client to essentially maintain a bunch of these local snapshots at different versions. And then the Graft storage cache will just maintain and keep around the pages that we need to keep around in the cache, while invalidating pages that we don't need to keep around anymore. So it has like essentially a garbage collector that just goes through and just maintains and curates this local set of pages. And then when a fetch comes in, so when the client says, hey, like I really need to read page number 5 at version number 10. Basically, the first thing it does is it goes and looks locally in the cache, like, do I already have this page? If it does, it just immediately responds with the page and the client moves on. But if it doesn't have that page, or that page has changed since the last time it updated, and this new snapshot version the client's reading at is pointing at a version of that page that it doesn't have, that's when we have to go to the server. And so the fetch process goes through what I call the oracle. And this is because Graft is like a lazy and partial replicated system. We don't want to force round trips when we don't have to. Like if the client's reading 50 pages in a row and doesn't have any of those 50 pages cached, we want to be able to do at least a best effort of minimizing the number of round trips we go to the page store. And so the way we do this is we use something called the prefetcher or the oracle. And I implemented an algorithm that I found that showed fairly good results on essentially predicting. It's able to pick up really common patterns. So it's able to pick up forward and reverse sequential reads, but also forward and reverse strided reads. And it was benchmarked on the Linux kernel using like remote access memory, and found that like in many workloads, and especially relational workloads, it performed really well. So I just implemented that paper. I don't want to like overthink things. It works for Linux running like Memcache and Redis. Like it'll probably mostly work for me for now, at least. And I've tested it and it works really well. So long story short, the fetch comes through into the Oracle prefetcher. The prefetcher expands that fetch for a single page into potentially a fetch for a bunch of pages. And then sends that to the page store. And the page store is really simple. The page store is like, do I have the segment cached in like memory? Do I have the segment cached in NVMe? Do I have the segment? If I don't, then obviously the segment exists in object storage or there's a bug. And it goes and gets it. It's like a tiered storage system. Downloads the segment and essentially materializes the pages out of the segment to the client. And so this is the entirety of Graft. Like as of right now, if we go back to this slide, like that's the core loop that Graft goes through that allows us to make this all work. So any questions before I do a demo? One question, and then we don't have too much time, so I'll have to do the demo.
Hi. You mentioned the rollups. Do you calculate the rollups on the metadata read every time?
Yeah, so when you do a poll, the metadata server calculates the rollups. To do this efficiently, I wrote a small set optimized alternative to roaring bitmaps. So if you're familiar with roaring bitmaps is a like compressed bit set essentially, or bitmap. It's really popular in databases. It works really well when you are dealing with lots and lots of bits and you want to compress them. However, it does not work when you have small numbers of bits that are highly sparse. It's like worse than essentially just storing a list of ints or equal to. So I wrote a custom bitmap, compressed bitmap representation. And one of the convenient things about it is it allows me to do intersections extremely quickly, and it's entirely zero copy. And so essentially I can map directly, like pages directly from object storage directly into memory without doing any deserialization. I can do a little bit of validation just to verify that I'm not like corrupt, and I can immediately build a intersection or a union of a bunch of bit sets and then send them to the client. Because I'm writing Rust and my client's just Rust, the client runs the exact same compressed bitmap code, and so it actually just receives these like bits directly over the wire, which it then can map directly into memory and perform bit operations on. And so with this compressed bitmap representation, my poll architecture is really, really cheap, like from a CPU and memory perspective. All right, guys. This is the fun part. Okay, so we don't have a huge amount of time, so basically, okay, well, let me remember what I was doing. So the first thing we have to do is we need a meta store, so let's go ahead and do that. We also need a page store. So because demo gods and because time, I'm not going to run this like in the internet. So we're just going to run this localhost. So on the left side here, I have my meta store running. So this is that component at the top of the diagram. And on the right side, I have the page store running. They're both just running against like essentially a local object store, like think like Minio sort of thing. So everything is just local, just to be simple. And we're going to jump over here. And we're going to run two SQLite nodes. So this is going to be our P2 node. And this is going to, oh, nope. Okay, we're going to just ignore that for a second. Go ahead and open up those. Get rid of you. Just ignore me while I do this. Okay. Okay, let me not control R my way to this terribleness. Okay, this is going to be P1. This is going to be P2. Yay. Okay, cool. So we have two SQLite nodes. The left one, right one, they're both empty. I can just confirm that before I CI myself. What we're going to do is load a data set on the left side. Okay, so this happens very fast on localhost because it's localhost. But what we're going to do is, oh, that's too many things. Okay. So what we're going to do is run this query on both. So what we've done really quick is we've created three tables. Two tables, I lied, two tables, accounts and ledger. We've created that on the left side. Graft's done all the magic we talked about. So on the left side, it issued those transactions, it uploaded those pages, issued a write on the Metastore server, and then on the right side, we pulled those offsets. We saw those things, but we stopped there, right? It's partial replication. So on the right side, we see that if we look at all the pages that we know about, we see that they're all pending. They're just chilling because we don't need them. We haven't issued any queries. There's no reason. So we're going to issue our first query. It's going to be called tables. And if we issue it twice, because SQLite's not cool about metadata that's out of sync, we should ignore that error. We're going to issue that, where you guys see that we have the same tables on the right side. But when we look at graph pages, we're going to notice that we've only downloaded a single page from SQLite, right? So this is like the fundamental thing. We have partial replication. We also have lazy replication. If we issue a query, so let me just go ahead and go down to the bottom of this file. We're going to issue a query, and notice that we're saying where ID in 1, 2, right? It would be really annoying if this downloaded all the pages, because it's not useful to download all the pages to issue that read. Notice that we've downloaded 2 pages, right? Now, why 2 pages? It's 1, 2. Let's just think about B trees for a second. B trees are trees, tree data structures. At the top, we have like these nodes that essentially have very high fan out. And on the bottom, we have these leaf nodes that actually store rows. In this case, we downloaded the B tree root of the accounts table, which is essentially this page with a super high fan out. And then we just downloaded the 1 page that's relevant to IDs 1, 2, right? So that's why we have 2 page reads. Now, again, Graft is multiplayer. So we're going to go ahead and issue a write over here. And we're going to issue a write over here. And then we're going to issue that same query. We're going to see that we got the state we expect, right? So when we originally ran the query, both accounts had $50. We issued 2 writes in 2 different places. Both writes took $10 out of account 1 and put it into account 2. And we are left with, of course, the result we want, $30 in one and $70 in the other, right? And this all happened extremely fast. And the reason it happened very, very fast is because it's on localhost. But in the cloud, the actual cost for this is relatively the same, plus the latency of waiting to commit to object storage. That's about a second during that commit process. And then the latency to pull, which says, we're not going to pull super, super frequently. Maybe we pull every second or whatever that duration is. But once we get those offsets, we can immediately get those pages, and that operation is very, very high scale out. And that's because of S3, right? So S3 gives us this very high throughput and very, very, very high scale out. So anyways, this is Graft. We'll do a couple other sort of fun things here, just to sort of look at various semantics. We just ran like a query that says gives us the top 10 accounts by balance. And again, if we look at Graft pages, we see that we invalidated, of course, a couple more pages, right? This is pretty much the most of what I want to show. I do want to show this graph status thing. So, during development, when you're working on synchronization engines and replication engines, you have to think about the the point in like the global timeline every client is. Essentially, if you think about like you have this global timeline, which is like the snapshot version log, but then you have like the local timeline of like all the different points each client read. And this gets very interesting to think about. There's all these optimizations you could do, but I came up with this nice little syntax. And so this one line, snapshot 414 4R4, encodes a lot of details. It tells us that the local LSN of this node is 4. There are 14 pages we know about. And the remote snapshot 4 maps to the local snapshot 4. And anyways, just a fun little detail I wanted to share because it helped me so much in developing Graft. I think that's the end of the talk. I want to leave maybe a little bit of room for questions, but I did want to show that Graft does work, and I'm planning on launching it this month. And if you are interested in learning more, on the right, I have my Graft launch sign up, which if you want to receive an email when I launch, please put your email there. And on the left, I have SQLSync. If you're interested in the last project I launched and the project that will be using Graft, you can go learn about it. And I'm also Carl Sverre on social. I'm very happy to chat with anyone about this. I'm a huge nerd. I expect you all are as well. And yeah, thank you so much. Appreciate it.
Thanks. Thanks for the talk, Carl. If you mind switching back to the demo screen.
Oh, yeah.
Yeah, so I'm curious what happens when you type pragma graph pages. Does it actually check with the meta server, or does it?
So pragma graph pages is entirely local. So the idea of pragma graph pages is what is the state of every page, the particular LSN that we know about, like the latest LSN of that page, and whether or not we have that cached locally.
So there was something in the background that pulled the awareness that there are 14 pages.
Yes, exactly. So yeah, the architecture of Graft is very flexible. Like from a client-side coding perspective, like if you were integrating Graft into your program, Graft lets you choose whether or not you want to have complete control of the synchronization process. You can just be completely manual. You could say, I want to sync exactly at this time. I want these semantics. Or you can sort of say, hey, Graft, like do your best. And it will do like a background sync. And that's what I've set up with the SQLite extension, because SQLite doesn't give me a huge amount of flexibility or latitude on how I choose what I can do and how much control I can give the application. So it just works sort of out of the box, quote unquote.
Thanks.
Question over on the left side there.
Thank you. I have a question. If there's so you mentioned mobile apps and like web browsers and stuff like that. Is there a way to use it, quote unquote, safely with untrusted clients? Like if you mentioned earlier, for example, that a client has like full authority, they can like corrupt their state, for example. Is there a way to, which that's so useful for client applications if they can only make like statements about themselves, for example, right? Is there a way to to use Graft to do that? Like, is it like an authorization system so that like a user can only write to like certain tables that are namespace to them, something like that?
Yeah, this is a really good question. So Graft is designed first and foremost as like a building block for more complex and interesting systems. So I did not want to make Graft have all of those semantics because that just introduces so many opinions about how people build their applications. SQLSync, though, is extremely opinionated about this. Like it has its answer to your question. So SQLSync models writes as essentially appends to a client-controlled log. So if you think about, you have 10 clients, they're all writing, we can essentially write, each of them can essentially maintain their own like mutation log. And because they own their log, if they corrupt it, we can just like reject their entire log, be like, go away, you're a bad client, right? And then the idea of SQL Sync is that we just need to be able to replay all of these logs in like one globally consistent order, and then build a database that can be then efficiently replicated down to clients. So Graft provides that sort of foundation. With Graft, you could essentially have just like a serverless function just periodically wakes up, or even literally as a callback on like a Kinesis queue or something like that. And every time it wakes up, it can just like take whatever is being added to the log, apply those rights to the global Graft state, which is now essentially authority because it's now like owned by you. And then Graft will do all the hard work of like sending that data down to clients, making sure that clients can see like a partial version of the data, but also a snapshot consistent version of the data. So Graft is fundamentally a building block. You can also do authentication layers directly on Graft if you want to just have like volumes per user, and like if the user again corrupts their own state, like you can just sort of ignore them. But yeah, it's like S3. Like if you have access to the S3 API, you can do a lot of bad things. Thank you for the question. That was good.
Thank you for the talk. I'd like to understand a bit more the relation between the pages and the actual files on S3. You mentioned that you do batching, right, to be able to have fewer requests. And I think in this demo, in a production environment, I would expect, or not would expect, but it's totally possible that all those 14 pages could be in one file, right? And so you would download one file and basically cache all of them at once. But here we can see that you just cache one page individual. Does it mean you have 14 files right now on S3, or is it still like, yeah? Can you just explain that relation a bit more?
Absolutely. So Graft uses what I call segments. Some other systems use similar things called segments, but they aren't necessarily exactly the same. In Graft, a segment is simply like a collection of pages that have been uploaded by many clients into many volumes at potentially many different versions. So segments are agnostic to everything. They're literally just, here's a bunch of pages at some state. If in like a real scale out version of Graft where you're not just on localhost with a single volume, and in the case where you have like thousands or tens of thousands of volumes or millions of volumes, and they're all writing, each segment will potentially have thousands of volumes worth of pages in a segment. Now, to make all this like work and efficient, segments are limited by multiple sort of heuristics in terms of like scale, so they don't get too big. And then future work is your standard work that a lot of like LSM trees that run on object storage do, which is essentially you want to like merge and optimize data over time. So you start with these like highly sort of sparse segments where you have like many different volumes, many different pages, and pages from like all over the volume sort of index set. And then you want to end up with fewer volumes that are larger that contain less volumes. Like you want to sort of move data around in a more efficient way. There's also the question of essentially like lifetime, right? So like Graft, ideally you have all these different volumes, and they all have different lifetimes. Like you might delete a volume, and like what happens when you delete a volume? You want to go back and eventually like clean up all these different pages from all these different segments. And so like LSM trees sort of handle this via like a combination of like tombstone records and also mergers, which essentially go like you just defer the deletion process until later. But the long story short, like to I think answer your question, like we want to have these files be as like dense as possible. And we want to optimize them over time so that they're efficient to access. And we want to organize them. So like going back to Nissan's talk, like we want to, so internally in my segments, I use a couple different data structures to make it very efficient to read like a subset of the segment into memory, right? So even though like the segment might be very large, it might contain like many different volumes, if I only care about like one volume or even just like a couple pages, I don't actually need to read the entire segment into memory. And a future work is that I don't even have to download the entire segment from S3. And so I can actually start to leverage S3's like offsets, the ability to read a partial file from S3. If you have like really good metadata and you're really careful about it, you can actually start to leverage that to just reduce the cost even more. So there's an entire group of like literature around this particular problem, and I'm trying to implement as much as possible by myself. That's the plan. Any other questions?
I had a quick question. Sorry, was there a question over there too? Oh. I was curious if you could talk more about this, like, you seem kind of excited about the diff algorithm that you're doing to calculate, okay, what segments am I looking for, and getting basically what the Metastore does to determine what you're missing and compare it to like what's the latest and everything.
Yeah, so similarly to the segments, again, like a lot of what makes Graft work and efficient is how we store commits in S3 and how we can efficiently replay those commits and quickly build up cumulative representations of change. So to do this, again, I wrote like a custom compressed bitmap data structure called Splinter, which is similar to Roaring but designed for small sparse sets. And this data structure I can essentially map directly out of S3 into memory on the Metastore. So I can take these like relatively small compressed blobs, map them into memory, and then using efficient like CPU instructions, I can essentially merge them into one set. I'm trying to think about your question in terms of like where I want to go with that. You were more curious about the algorithm to do this, or
curious about more details on that process.
Yeah. I mean, it's really like if you just think about, if we get rid of the compressed representation, if we just think about the bit set perspective, like if we just have, if we notice that, like, let's say that the volume is fixed to like 1,000 pages, you just can't have anything but 1,000-page volume, we can essentially represent that page set as essentially a single bitmap with 1,000 bits. So that's essentially how my system works. Now, this sucks because now all your volumes are 1,000 pages. We want to be able to be flexible. We want unlimited or like close to unlimited amount of pages. We want different size volumes. So to do this, we use a compressed bit set, which allows us to store 1,000 bits in a way that is both compressed and also allows us to store 2,000 bits in like the same data structure. I don't know. I'm not explaining this super well.
Very cool. Very cool.
Yeah. I will release Splinter open source. You can read the code. Don't read the code. I think there was another question somewhere over this general area, or maybe over there. Does anyone raise your hand if you have a question?
Yeah, actually, a second question. So I was wondering, so one of the reasons, for example, why we use object stores, I presume is usually because we can then like basically just pay for the bandwidth once and we stream it directly from S3, right? Is there a similar way, because when I looked at the graph earlier, like all of the blocks themselves went like through the page store. So if I were a client, I request like a page. Is there a way to basically get the equivalent of like a HTTP redirect from the page store back and actually stream the page itself from S3 directly?
Yes, that could work. However, that actually is not what we want. And the main reason is permissions. We can't enforce, like, because our segments potentially contain volume rights from many different volumes, we want to be able to ensure that like a client who only accesses volume 5 only sees the pages from volume 5. The second thing, though, is that like the page store is stateless and runs inside Fly in a heavily distributed fashion, and has no consensus overhead. And so essentially the page store has like a close to like one-to-one relationship with the actual backend S3 like read sets. And so like the overhead is almost none. Like the page store is essentially streaming through, and the page store actually improves our performance because the page store stores all the data that it retrieves on in an NVMe LRU cache. And that allows us to like dramatically increase the performance because we see like high correlation. The Graft is ultimately designed to handle like the thundering herd problem where you have like 10,000 devices and they all want like the latest update. So Graft doesn't want to have all those updates streamed through like one node. Instead, we stream through 1,000 page servers connected to like 10,000 S3 nodes. And it works really well. Like S3 is really good at this.
Thank you.
Raise your hand. Now is your chance. No? No? Cool. Well, thanks everyone for listening to me talk about something I worked on for a long time. I'm very passionate about it. I'm very excited about talking about it. So if you have any more questions, please connect with me.